Welcome to video 5 in this MLB workbook series, which deals with machine learning, specifically genetic algorithms. So when we finish this video, we'll be able to basically generate predictions using the MLB workbook's genetic algorithm. I don't want to make this video too long or make it an academic treatise into genetic algorithms, so to get a better understanding of the mechanics, I would suggest you look at a few videos on YouTube, starters, tutorials on genetic algorithms. There's so many good ones out there that you can get a real feel for what we're going to do. But what I'm basically going to do in this video is explain briefly the structure of a genetic algorithm and the processes, and then we're going to have a go at the workbook to show those who want to try and get on board using it with a minimum of knowledge, so that they can do so. So basically this schematic here represents the genetic algorithm process. The actual genetic algorithm is modeled on biological processes, on the Darwinian theories of evolution, specifically survival of the fittest. So what we have is a population of chromosomes competing against each other. The fittest ones get to procreate and produce the next generation, and that generation then competes with each other, produces another generation, and as the population of chromosomes evolves in its ability to predict fantasy points, we reach a certain point, either we run out of time or a certain level of accuracy or a certain number of generations, and the algorithm ceases and you have your answer. I know that's quite an abstract representation, but let's just go through it in a little bit more detail here. Firstly, creating the population of chromosomes. What a chromosome is, and we'll get into detail on this later, is an algorithm which has the ability to predict fantasy points using a past data set of historical data. There might be in a population 50 or 100 individual chromosomes. When they are created by the workbook, each individual chromosome is uniquely different from its neighbours, thus giving the population a level of diversity that's required to complete the task. The first step in the generational loop is for each chromosome to predict fantasy point scores, and then have their individual predictions tested against the actuals over a period of 30 or 60 days prior to execution of the algorithm. The more accurate the individual chromosome is, the more fit it is considered to be for the purposes of procreation. So what happens next is we then take the fittest members of the chromosome population and we allow them to switch their individual genes, two parents basically combining, or crossover as it's called, and producing one child. Now that child goes into the next generation. Essentially, if you have, let's say you have a population of 100 in the current generation, the crossover process is done 100 times. So we deviate slightly from biological practice here, in so much as once one child is produced from two parents, those two parents disappear. So in essence you have 100 crossovers involving two parents, and 100 children are produced, and they become the population of the next generation. And so we go round the loop and we repeat the process of checking them for their fitness, and then building the next generation, and so on, until a certain time or a certain number of generations has passed, and we exit the program with the best possible solution to the problem. So that in essence is what we're going to do. Now I'm going to take a break from description now, and I'm going to go straight to the workbook so that we can see how you can do that practically, and those who are less interested in getting into the weeds of this whole issue can then try to use it at their leisure. So let's go over to the workbook now. Now I appreciate that the explanation I've just given is a little abstract, so for those who prefer just to look at how we do it, we go to the machine learning section of the program. The first thing we have to do is we have to download historical data, so that we have some historical data for the chromosomes to process, and for us to gauge their accuracy. I'm not going to do it now because I've already done it for today. This is what it looks like. It's a data set representing one player's participation in one baseball game on a certain date. Every column of this data set represents facts that were known prior to the game. So by that I mean we knew about Nolan. We knew he played for Colorado. He was third base on the 21st of April. We know what the Vegas money line guys say his team's probably likely to score, what the opposition will score. There is one column in this whole data set that is not known on the day in question, and that is the FanDuel points that will ultimately be scored in this fixture. So the chromosomes will use this information. They will use everything here to try to estimate the figures in this column, and then we will be able to determine how accurate the algorithm is, and judge their performance on that basis. So there we have it. We've got all the latest data loaded up, and then we set up the genetic algorithm. Basically, quick description here: the number of chromosomes in the population, too small and you won't get the diversity and the population will die. Mutations we'll deal with in detail. The maximum number of generations, we discussed generations earlier. This just puts a cap on it, although you normally time out with the hours between betting. You can easily run these for more than a day. Historical days back, that simply means how far back do you want the chromosomes to predict for the purposes of measuring their accuracy. I like 60 days, but it takes a long time. Elitism we'll deal with in more detail after this quick demonstration. Step through just means if you've got 60 days worth of records, that can be 20,000 records. Stepping through them, doing every other record or every third record, simply means that you get through it faster. Time is a problem with these types of calculations. Okay, so quickly flicking to the genetic algorithm. Okay, so to run the algorithm, all we do is we simply go up to here and we press the run. It warns you that we'll erase everything here. Don't want to do that now, but imagine that we let this run and we come back 12 hours later. It runs overnight. Here's a good example here. This is on its 7th generation. It found the best solution on the 7th generation of a fantasy point error of absolute error of 2.2. Every generation took 146 minutes to calculate, so obviously you can do it a lot faster. You can experiment with changing the settings. For example, if I went back to here and I changed this to wherever it was originally, if I change that from 3 to 6, it would halve the time because we're stepping through the records. If I change that from 60 to 30, it would halve the time again. So if I cut down the population by half, we start to cut into the diversity there, and we might have problems, but once again it does cut down the time that the algorithm will run. Let's say, for the purposes of getting a good result, letting it run 12 plus hours is quite normal. I consider this to be a good result. I consider 146 minutes to be a good time per generation because I really like to process a lot of data. So now I've come back the next day, imagine. I press stop algorithm, everything stops, and all I have to do now is simply leave it, and when it comes time to use these results, I'm doing what I normally do here. I do a bit of my linear regression. Once I want to go and get the predictions from the genetic algorithm, I firstly make sure that I have fresh data here. So once again, this has been updated today, quite recently, so I'm good with that. So once I have this data, and that's important because the algorithm is going to switch from using historical data to today's data. I then go back to here, to the genetic algorithm, and I simply go down here and I say transfer best predictions to the solver. So if I press this, what it basically does is it says, okay, here we have the best condition, and we'll learn more about that later. So all I do is I press transfer. Might take a minute. So right, we go to this, and now what it's going to do is it's going to calculate using today's data the predictions for today, and it puts them in that column there. This is our live column. Would you like them transferred to the solver? Yes, please. Transfer complete. Do you wish to upload your results to the API? Normally I hope you'll say yes, but if you want to say no, then there we go. Now you simply go back into the solver, you run the filters again, and you will now be using predictions. The best prediction produced in that 12 plus hours by the genetic algorithm has been recalculated for today, and there it is. So that in essence is how we do it. So if you're one of these people who doesn't like long-winded explanations on how this works, the real detail, you now have enough information, I hope, to basically use it. What I'm going to do now is I'm going to go back to the PowerPoint and really get down into the weeds of how things are done in this algorithm and how you in fact can reprogram it should you want to be a power user. Okay, so let's look at this process in a little bit more detail now, so that we can take our understanding to the next level. I sort of blithely said earlier that we create a population of chromosomes, and that every chromosome is a freestanding algorithm that can calculate fantasy points. Let's take a look at one individual chromosome and what it actually looks like as a member of this population. Okay, so this is essentially what a basic 10 gene chromosome looks like. Now, all of a sudden you can immediately see that this is not enough information to start predicting MLB predictions. However, you'll notice that there is an extra function I'm going to introduce at this moment, and what basically happens is this is the genetic code, and initially when we set up the population of chromosomes in our code that we're going to see in a minute, we use this function to ensure that every individual candidate in the citizenry is unique. For example, MLB gene, the first argument is the gene ID. This is 1. So gene 1 is here. And when this gene is used in the code, if it hasn't been initialized, it will give a value. It will have a value of between this lower number here, 0, and this upper number, 1. So that, as you notice here, it's 0.151. Gene 2, to generate gene 2, that would be a 2. Once again, that's between the low of 0 and the high value of 1, 0.204. So this is the heart of the chromosome, and if we have a population of 100, we would have a matrix of 100 of these chromosomes, all with different values. So maybe gene 1 is 0.15 here, maybe it's 0.23 on the next, 0.56. As long as it's between 0 and 1, that's what will be generated. So that's how we create the population. And let's have a look at how this chromosome group is incorporated into the code. So back to the workbook. What we need now is we need what's called the developer ribbon. If you don't have this up as default, just hit any other ribbon, right click on it, customize the ribbon, and if you see down here developer is selected, that's normally deselected in most default conditions of the ribbon. So now we have the developer up, we're going into the section of the workbook that stores the VBA code, that's Visual Basic for Applications. We click on here. When you first open it, it will look like this. You'll have all the worksheets here, some of which you can see, some of which you can't, and then you'll have down here a section called modules. So the module we're interested in is quite rightly called your code. This is the only module you have to go in to edit or rewrite the individual chromosome code. So if you remember back in the schematic, we had a collection of, I think it was 10 chromosomes. Of course it can be as many as you want to program. It can be up to, I think the maximum's like 20 or 30 or something. But basically, if you look here, what you're actually doing when you call a member of the community, a chromosome, you're calling your fantasy point prediction, which is a subroutine in VBA. Now, I don't know how far to go here. I'm assuming you have some knowledge of VBA by showing you this. If not, it's really quite easy to follow. So if I look at the code here, it's similar to the regression analysis in that we use functions which are actually identical. We're just writing them down. So the code calls this routine every time a member of the citizenry or a chromosome wants to predict the performance of a player. So if we just look here, simply the base average is MLB underscore gene 1 value 0 and 1 times MLB moving average for 30 games. So we've seen this structure before in previous videos. What it's basically saying is multiply the gene value of gene 1 for this particular player and this particular member of the community, and then calculate the team score using the same. And if you look down here, for example, if the win flag is true, then the win correction is MLB gene number 2, and that can have a value between 0 and 10. So what I'm saying here is, I don't want to dwell too much on this, because what I'm going to do, if I get an encouraging response from this video, I'll do an advanced one that shows you how to reprogram this. But let's just leave it here saying that the combination of the collection of genes, which is the chromosome, acts through this code here to produce predictions. And if you notice, if you did the linear regression one, you also notice here we've switched, we've cut up the predictor for P, which is pitcher, and also we've got else, player is hitter below this line. So, and all the way through we've got all the way down to, I think, gene 10 there. Of course, if you program longer you could have 20 genes, but this is like the default calculation that allows anybody to use the program. So that in essence is what you do. And if you are a VBA programmer and you want to use the functions, right at the top of the Your Code module is a function library for reference. You've seen all this before with the estimator in the spreadsheet format, but this is just doing it in code. So okay, that is in essence how a member of the community, a chromosome, generates its predictions. Okay, so basically code plus the chromosome bar is one member of the population. Okay, so let's imagine we have I think in the previous example of the workbook we had 75. So we have 75 of those units all generating their own predictions. And remember, because gene 1 will have a different value for every member of the community, so will gene 2, etc. You're going to get unique prediction sets from every member of the population. Some will be good, some not so good, some will be really bad. So what we then do in the next part of the program is we now have to decide who gets to be the parents for the next generation. And by that I mean the fitness. The fitness is determined of every individual by the accuracy of of their predictions. So the lower the absolute mean error of their predictions is, the greater fitness they have. So let's just look at that. How do we decide? Well, this is done mathematically in the code, but basically what it's done with a random number generator. But imagine a situation where you have a population of 5 citizens. Their proportion of the slots on the Wheel of Fortune is proportional to their fitness. So in this example, citizen 2 would have had the biggest absolute mean error in fantasy points, so its predictions wouldn't have been very good, so it gets a small section of the wheel. It only gets here it's 1.5 slots. In our actual practice, it's a unity number of it's an integer number of slots, but I found this diagram somewhere, so I'm using it. Conversely, citizen 3 has a really small error, so it gets a big chunk of the slots. So whenever this wheel is rotated and the random slot is chosen, the roulette wheel is, as it's called, it's the roulette wheel method of selection. The chances are that number 3 will have a greater opportunity to be a parent than number 2 or number 4 or number 5, and the second one most likely to be a parent will be number 1. So if you have a population of let's say 75, this wheel will be rotated 150 times, because the first rotation will choose parent 1, the second rotation will choose parent 2, and let's say probability says that maybe it will be 3 and 1, and they then are combined to produce one offspring. And so then that will happen again and again and again until you have 75 offspring. That doesn't mean to say that poor number 2 here is a very weak member of the community, doesn't get the opportunity to procreate. It simply gets a much smaller opportunity than the other stronger members of the community. So that's what we call crossover. Basically 2 parents coming together, parent 1 and parent 2, to produce one child. And the way the child is produced in this specific algorithm is you take the first half of the chromosome, so the first 5 chromosomes, or if it's 11 chromosomes in your code, it might be the first 6 and then the next 5. But on this example, the 5 green ones come down here to the child, and parent 2 provides the balance of the chromosomes, and there you have the first member of the next generation. Unlike our biological world, the parents disappear at this point. So remember, we have 75 members in generation 1. Once this child is produced, we do the calculation 75 times, and we produce another 75 members who have spliced DNA. And so the parents effectively die, which is, contrary to biological practice. Our parents go away and rent RVs and go into retirement. In this case, only children come out the other side. There is one exception to that, and that's called elitism. If you allow elitism in the initial setup of the program, say you have 100 members of the citizenry and you set elitism at 1%, the one parent who is the most fit is allowed a free pass into the next generation. So 1% elitism, in a community of 100, the next generation will be the strongest parent and 99 children. And incidentally, with the lottery wheel method, of course, if this is citizen 58, who happens to be particularly strong, and this is citizen 34, the lottery wheel means they can have as many offspring as the random number generator decides to give them. It's not like once you've given birth to one child, you then stop. One parent can give birth to many children depending on its relative strength in the community. So that's how that works. And one other thing, we've talked about elitism. That's one way you break the chain and you carry through from generation to next generation. Mutation can be very valuable. If you have a population of 100 members and you set mutations at 1%, then every single chromosome will be grabbed from a member of the population, depending on, randomly grabbed just by a random number generator. So gene 1 could come from citizen 10, gene 2 from citizen 28, gene 3 from citizen 33, etc. And the only limitation is the initial gene setup. If this was originally set up with a minimum value of 0 and a maximum value of 1, whatever goes in there, because it's already in the gene pool, can only be between 0 and 1. So it's kind of a controlled mutation, but it will be so jumbled that it can either be very strong and very good or very negative. Most of the science fiction that deals with mutants tends to look at them in a bad way, but there are in fact good mutations, and that maintains the population diversity, and it also opens up new avenues of solution for the whole community. Okay, so having dealt with the detail behind it, let's go back to the estimator and let's go through these individual points. That's kind of self-explanatory. Total genetic population, 3% mutations is somewhat high. I would do, well, I can't say this is a good thing or a bad thing. The more mutations you have, the more chances you can kill your population. It's a bit like if you have 100 people who decide to live on the site of the Chernobyl reactor, then they might not exist for more than several generations. What you're looking for in the setup here with mutations and elitism is you're looking for this sort of curve of evolution where the curves have a distinct profile. This is the average fitness of the population, and because we're dealing with absolute errors, as it gradually goes down, that shows that the population through successive generations is getting fitter, it's getting better. The lowest solution, the lowest error for every generation is the best solution. So if I were to put mutations too high, I might expect this blue line to start going up, where the population gets less healthy. That's not good, because you're not, ultimately we're coming towards a solution here where all the population gets healthier and we take the best of the healthy solutions. The lowest one here, if you see, the best absolute mean error is 2.2, which is pretty low, and that occurred on generation 7, so that's the generation up here that was still cooking when the command was executed to stop. This other line, diversity, if you have too many genetic mutations, you do need to maintain diversity. If you have zero diversity, your population will die. You can actually kill the population in a genetic algorithm, in which case you get no or a bad solution. But once again, the diversity is gradually coming down here, so I've probably got, the right amount of mutations. The other thing to note is this doesn't anywhere go up. So this was 2.29, this was 2.59. It's gradually getting better. One of the reasons for that, one of the reasons it can't get worse, is I do have elitism set. If I had elitism at 0, then it is possible that my population could go into the dark ages. By that I mean, the best solution could start rising, and I in fact had the best solution at 1 or 2 and not 7 like we have here, allowing the most fit member of one generation to pass through, as elitism does, means that you cannot possibly get a lower, better result in the next generation. Or let me put it, you could not get a less healthy result in the next generation because you've already let that good guy through. So that's something to know. Also, I only have 75 here, so if I set elitism at 1, well, 1% of 75 is less than a single person, so you might not get anyone through. So that's why if I only have a population of 75, to get 1 through, I probably have to set that at 2. Once again, here it says mutations generated were 2. Okay, so let's just go back here. I think we've already discussed the historical days back. Step through. Let's do this now. Now you've all seen what's a good profile. We know that this one, time per citizen, took 2 minutes. And each generation took 146. What we could do now is, if we just look at this and we say, okay, I only have 10 citizens, I only want them to go back 10 days, and I want to skip every 10 records. If I run this, you'll automatically see that rather than taking 146, or before I do this, note this. This, of course, is the diversity. This is just the relative, the errors of all the population. If you see that sawtooth, do you know you've got some diversity left? Okay, so let's just do this. Oh, historical data is 7 days old. Okay, I would normally go back. I would normally stop this. And go back and download the historical data again. But you see how we're ripping through. If you look up here, we're already on citizen 10 of 10. Okay, so we've already gone through the first generation. We're now on the 4th generation. Of course, the result here is probably going to be rubbish because we're hardly, we're only looking at 350 records. That's interesting. So what's that? Oh, okay. You notice here, because we don't have elitism, well, we only have elitism at 2%. So 2% of 10 people in the community is not even 1. So you notice here how the lowest, we've actually had a retrograde step here. Although the community did initially get healthier, I'm seeing the diversity has gone down incredibly, we don't have any mutations. So this basically is not going to produce a very good answer. Now, but we're already up to generation 6, 9. Okay, so let's stop that. Let's go back to, if I've got the time, and quite often I run this on another laptop. Incidentally, I forget to tell you on this, if you've got the same, if you have the same algorithm here on different copies of the machine, and it will be the same unless you get into programming in it and changing it, all you have to do to take the value of this is you simply need to go down here and you pick off the values of the individual genes in the chromosome. You copy those. You can copy those to your live copy for that day, and when you actually press this button, it simply says, okay, I've got all my best gene values here that took hours to get. I'm now going to recalculate them using the data. So the point I'm making is the only thing you need to know is that. What I do is I have another computer in my office that works up to 24 hours sometimes, and all I do is I copy the values here, I put them in my live copy I'm betting with on my everyday laptop, and all of a sudden I've got the product of that 24 hours of processing. Okay, so anyway, let's just go back to, alright, so that's realistic. Mutations, I want maybe 1, so that's 1%. That's 1 in 100. Maximum generations, I never get there. Historical days back, I like 60. Elitism, gotta have some elitism. Alright, let's try 2. Although I tend to say 1. Step through players, I don't like any stepping if I have to, but all that does is it uploads the results to the API. If you leave it at no, I would like the default to be yes, but you know, you might want to load up your linear regressions instead of your genetics. So anyway, we've got this set up here. Step through every 60 days records. Now if I say run, okay, I wouldn't, once again I'd stop here and get the latest data because I'm investing time. Now if you look up here, now we've got 13,000 records to run through, and look how slowly we're running through it. I'm going to say that this is going to be 2 or 3 minutes per member of the citizenry. So we might be looking at we might be looking at 200 or 300 minutes for one generation. So what's that? That's 3 hours per generation. I'm not even going to make you watch this. So the longer time spent, the better result, but you need to have maybe another laptop to cook it up like this. Stopping, command executed there to stop. Okay, I think that's probably about it, because now you already know that all you need to transfer over is you press this and then it brings it over to today's calculation and you're all good. Okay, one other thing I just want to point out, if you do like to change this up a bit, just remember that let's say for example you wanted to change in the hitter section here, we have op score remmed out. That's not an active line of code. If you wanted to change it, say you wanted to put op score in, so what's the top gene? Top gene's 10 now, so I want a different one. I'm going to put 11 in. Then you would just put here plus up score correction. The reason it's not in is I'm not so sure the opposition score has any validity in the structure for a hitter. But you can just mess with this, and as long as you name the genes consecutively, see, I'd use 10 there, now I've got 11, or if for, and I'm not even sure why you would ever want to do this, if you wanted the same correction on team score as up score, you could do this. But the reason I'm here is I want to point out that the minimum and maximum values on the gene can save you a lot of processing time. Let's just rem this out. Okay, so now that will be 0, so that makes no difference. If we go up to a more obvious one, base average, some people just use that function, moving average for 30 days, as their prediction. So if I were to put in that gene there, because that gene's multiplied by that, if I were to put in here a value of 0 and 10, what this would mean is, or even worse, minus, whoops, let's say a value between a minus 10, nothing there would not say that the genetic algorithm would eventually evolve to produce the same result. But the problem here is one would expect that if you're using a moving average fantasy points, then maybe you should restrict it to a maximum of 1 times, or maybe 1.1. That will be closer to the answer than 10 times, because if this is a pitcher and he scores an average of, let's say, 40 fantasy points, we know there's no hope in the world he's going to score 10 times 40, which is 400. So always remember that, or he's not going to score minus 400. You can steer the algorithm towards success by simply saying, okay, these parameters are the same. Also, here's another one. The win correction, we know from previous videos that I think FanDuel gives something like 6 points when a pitcher wins a game. So the win flag is true if the Vegas team score, the Vegas predicted score, is greater than the opposition score. Okay, that's quite simply, if Vegas thinks they're going to win, the win flag will be true. But then on the gene, I've got here a correction between 0 and 10. That means I'm thinking about 5 might be awarded by the algorithm. If I put between 0 and 100, well, I know that I don't want the award for Vegas telling to win to be 100 points. It would be silly. You follow? So once again, make sure that the gene minimum and maximum values are commensurate with what would happen in real life. Home or away correction, I think it makes about 3% difference. So the HORA coefficient I've set up, and once again, if you skip videos you might find this confusing, but and this is all written down, the home or away coefficient on this workbook returns 1 for home and a value of -1 for away. So when I use it here, if I think that where is home or away coefficient, okay, so I've said on this gene I want the correction to be between 0 and 3. So what it will be is, if this guy's at home, it will be 1 times a value here between 0 and 3. So I'm expecting maybe the final solution might be closer to 1 or something. But I'm not going to put here 30, because there's no way you should get 30 points extra for being at home. The data doesn't reflect it. So having said that, as I say, if I get feedback that says please give me other options as to how to program this, then I might do another video, but I don't know whether people are just going to take it as a black box and run with it, in which case this is not a bad algorithm, but it'll be the same as everyone else is running except those who program. The top of this Your Code module has the reference library, so take a look at that, and it will give you lots of new ideas. Alright, I think, having said all that, we've probably discussed enough to allow you to not only run the genetic algorithm, but to be a little bit creative. So once again, hope you enjoyed this video, and good luck for your betting, and if I need to go into more detail, I'll do a more advanced one at a later date. Thanks for listening again.